I'll be watching the Twitter feed.
Okay.
But if you can mute yourself now, we hear just a little bit of an echo. So.
Okay, I'll turn off now. Thanks.
Thanks.
No worries. You can hear me? Wave, I can see you waving if you can hear me. There we go, good. Hi, my name is David Robinson. I am a high school teacher at a place called Toronto District Christian High. It's just north of here in the Woodbridge area. So it's a nice small school. We have about 400 students, which is unusual for our area. And the fun thing about teaching there is that you know all your students, you know the staff. One of the hard things about it is that often you end up being asked to teach things that were perhaps a little outside of your discipline. So my background was in fish. I teach physics almost all the time and geology for a little bit. And so at the beginning of my career, I was asked to teach chemistry, which is technically a teachable of mine. In the first couple of weeks in, we found out that they needed me to teach physics as well. I was both departments for one semester, which was a little scary in your first year. Usually that goes, hey, you should teach all the grade 9 applied kids, which would have probably been an easier transition. But one of the things that I've learned from it is that it's really important for us as colleagues to support one another. So right off the bat, both for those attending the conference as well as those our friends up in Northwestern Ontario, that makes it a bit harder to join us here. That's my email address. It was tough at the beginning of my career to feel like I was a little bit alone. And so you're not. If you're struggling with remembering a part of the model, come on in. This is the grade 9 current electricity workshop. If you're struggling and can't remember an aspect of the presentation or have like not too fancy a physics question about basic circuits, Robinson at tdchristian.ca is my email. And I'll do my best to answer that within 24 hours. If you send me an email and hope for an answer within 15 minutes during the school day, that may be optimistic. So one of the things I was asked to do, I was just filling a bit of time before we actually got live. And there was a request for me to actually do it for this. So this has nothing to do with current electricity, it's just fun. So grade 10 optics, at some point you need to teach about the additive theory of light. That white isn't a thing, it's something your brain does, and that we can trick your brain with red, green, and blue to see any of the colors that we need. So right now that's white, supposedly. There's no such thing, and yet our brain is doing it. The fun thing is that the mirrors that are reflected or used for reflecting in here, for selecting your different colors of light, one of them in one plane, and if you do this in front of a regular light, it just looks like a gray shadow. Do it at 45 degrees and do it really carefully, it looks gray. And then, hopefully you can see this from your angle over there, it'll make a purple shadow in the other direction. And people were asking, well, where would you get one of those? So I think we can see that that's gray and purple in this screen there. I hope so. If not, you'll have to trust me. Where can you get those? Well, if you've attended the theater recently, now there are different models for this. This comes from a 3D home system that a student brought in that was broken that we took apart. The 3D ones for the theater are polarized a bit differently, but you still have polarizing filters you can pop out and play with. So, grade 9 electricity workshop. I'm indebted to a couple of fairly wild characters that have now since retired. Dave Erb and Doug DeLamater. Dave Erb up from Northwestern Ontario in Red Lake. Doug DeLamater from Barry's Bay, close to Algonquin Park. And so about 16 years ago, I attended this conference, attended this session, thought, these guys are nuts. I like it. I want to hang out with them a bit more. And so the next year I was helping them carry stuff. The next year I was helping wire. The next year I ended up starting to co-present, and then they retired. And here I am. So you're doing a dangerous thing by showing up. Perhaps you are going to be the next co-presenter and solo presenter. I don't get to retire anytime soon, so we'll get to tag team it. Okay, so that's how you can get a hold of me. Some additional resources. This isn't officially STAO sanctioned, but 5 years ago I thought there's a bunch of basic skills that I'm teaching my kids again and again and again and again. Bet you this would be easier if I just made a simple tutorial video that's got my voice on it, my equipment on it, for simple things like series circuits, parallel circuits, just basically how an ammeter and a voltmeter work, how to solder. And this is what I was expecting when I did it, my students. So over the last little bit, I've got about 400 people who have, well, not 400 people, probably about 80 students that have viewed how to solder 5 or 6 times each. And then something really weird kicked in and realized that a lot of people need help with simple circuits, series circuits, and parallel circuits. Because I've cleared 60,000 views, and that is not entirely my students. I'm pretty sure I think I would have seen them. So it's a resource that if you'd like to use it, enjoy. Some additional videos that I learned a little bit about tagging and the importance of proper tagging. So my schematics and reality going between a schematic diagram and a real circuit, they get to languish in the hundreds along with how to solder. Maybe one of these days I'll tag them better and people will find them better. But that's TD Physics. That's my channel. If you like it, good. If not, enjoy. So how does this workshop actually work? Well, we're going to give some handouts in a second, and they're going to be the very first example, the first sampler of how this workshop runs. And so the first section is going to be the teaching notes on how we actually present the model. And so that's going to have kind of the different grabbers, the different techniques that we use to try to explain it to kids. Then there's blackline masters that are ready for you to use. What is fairly common at this conference is people have been assigned grade 9 science. They've done the biology, they've done the chemistry, they're thinking, astronomy's looking good. How can we delay physics? And so if you're into physics real soon, these can be ready for Monday, for a couple of days from now. So you've got blackline masters. They come in Word format as well as PDFs. The Word format means that you can tweak them or modify them within reason. You can't sell them, they're Steo's resource, but for use with your kids, you're welcome to do that. And so if you don't like the way that something is exactly worded, myself, some of the blanks, I thought, you know, I'd like to give it a bit more guidance. Can you circle one of the two answers instead? And so you can tweak it to your liking. But for particularly for student teachers or new teachers to electricity, there's also full answers to the handouts that we have ready for the kids. So if that's giving you some anxiety. To get those resources, you go to steo.ca. So that's Steo's website. And then you come over to resources and you click on resources. There's a number of different options that'll come up, including les ressources en français pour nos amis francophones. So secondary is where you'll go if you're looking for these particular resources. So under resources, you've got a whole bunch of different options down here, but the grade 9 current electricity is the one that I do. And when you click on that, that opens up simple circuits, and then even these are broken down into smaller steps in terms of this is the video of how we worked together. And so we've got footage prior to this one of the legendary Dave and Doug team. When I manned the door to make sure that it was quiet for the videos, now I present it. And so that's Dave Erb, my science father from Northern Ontario. Not little father, but he's been a tremendous influence in my life, and I appreciate his work. So here you see that they've got the doc format, your PDF formats for those resources, reminders of how this lab went. So if you're like, oh, I don't remember how that passing thing went, you can actually, this entire session has been videoed before and has been broken into little segments. And then step by step for our first lesson and series circuit lesson, parallel circuit lesson, batteries lesson, and so on. And finally, we spend a lot of time saying that we are Steo APSO, but often our Francophone friends rightfully feel like we don't get as many resources into French for them. And that's particularly in Northwestern Ontario, Northeastern Ontario, where I'm from, Ottawa region and others. I've not met Madame Chantal Rieu, but I love her because she is fantastic. She went through and translated the series, simple series and parallel circuit lessons for us into French, which is something I've done a French presentation before. It wasn't pretty. It's kind of a broken Northeastern Ontario version. I learned up there. But she did a professional job of it, and very, very thankful for the work that she's done. Okay, so in terms of this, we're going to break up our time together. We're going to front load it with how we would actually teach the model. And at the back end, any theory, if you're a little fuzzy still on how electricity works at the end, or how to build. A number of people are very comfortable with building circuits and need a model to do it with students. And so we'll put the building towards the end. So that also compacts our time for people who are here at the conference and have time constraints and need to go somewhere else. So we're going to be doing that together as a group. And instead of our usual model of doing this with the class and then coming inside, doing pencil paper, two-dimensional thinking work, and then the next day doing building with actual batteries and switches and bulbs, and then cycling back through to series circuits, modeling, 2D thinking, 3D thinking. We're just going to do all of the modeling right up front together, and then we'll save all the classroom work for the second half. Okay. Any questions on anything we've done so far? Any questions from Northwestern Ontario? You're good? Okay, so let's model. Okay, so a couple little things. So in terms of what you need as a classroom teacher for this, you need however many kids you have in your class. On Thursday, I ended up with 42 or so. That's a little bit bigger than your average classroom. Today we've got about 2, 4, 6, 8, 10, 12, 14, 16. Nice small class, big enough for the model, small enough not to get too overwhelming. If you're new to teaching, there's a couple rules that you need to think of before you get kids to stand up and do things. Classroom management says, hey, you got to make eye contact, know your kids, and prep them before they stand up, because as soon as they stand up, they're gone. If you haven't prepped them already, unless you've got kids that I have yet to teach. So just kind of prep them in whatever way that you find effective. Mine is, there's a couple ways we can teach this. There's kind of pen and paper, I talk to you, or we can become part of a circuit. It's way more fun to do it this way. You know your kids in advance. You know the ones that are going to be difficult. Have the plan to isolate that kid from the activity or whatever it takes. But this is a fun way, and once the kids are into it, it does work well. So what I'm about to do, and this is going to take some coordination with our film crew, is I'm going to be heading to wherever that would be in your classroom, either bunching a bunch of your tables together. One of the other things that you could do is go into a hallway and do this. So depending on your confidence level that you have with your students to make your lesson look good or make it look like a zoo, you may decide whether or not you would do that in the hallway or not. But that's what we're actually going to do right now. So film crew, you two grab that and run. And the rest of you get to stand up, and you need to grab a block before that here. Yes. It can be. This breaks down into small lessons nice. Yeah, good. Okay, here we go. So my challenge at my school is that this is kind of my first day activity. At my school, we have enough kids that 4 teachers grab all of one grade level, and basically we all get to pick our favorite science. People are like, ooh, physics. Like, physics! Like, no, that's like the best one. Give that one to me. Like, ooh, that's hard. I'm like, hey, you enjoy your biochem, astro stuff. I got mine. But I don't know my kids when they come in. And so after learning their names, because if we don't know our kids, we're kind of not doing what we need to do. I teach kids. This is my subject. I teach kids. But I don't know them. And so one of my things I do is say, okay, I don't know you guys very well. Who's into pain? Which is a really fun intro for kids, because they don't know me either. Right? Pain. So who's in? There we go. We got our first volunteer. So I'm not sure if this is visible from there, but
came for farther than me, so if you want to get him.
There we go. So I'm going to tell him, you got to get one finger on each one of the prongs. Okay. So that's a little bit closer. There's 2 metal prongs right here. I touch them, and I think that's looking bright enough on the screen there. There's a flashing light and a weird sound that comes out. My students are never that brave, just go boom, they're always like, ah, and they bounce off. And so that's the fun one. So first of all, they've got a sense that there's something special about conductivity. Now, I always prime them. I teach in the center of the circle at this point, which does create its own adventures of you have your back to 1/3 of your students at all times. You need to learn to slowly rotisserie style be half-baked in your classroom, which I usually am. And so I say, okay, now normally by this point they don't have blocks yet. This is in the chairs, who likes pain, and then I get 2 kids. I'm like, ooh, okay, can you take that hand and put 1 finger on this side? And can you come a bit closer? Can you take that hand, your left, and stick on this side? That shouldn't have worked. Sorry, I was part of the circuit. Why is it? It's not. They're not touch buttons. They're not push buttons. You just touch pinkies on that side. If you ask kids to hold hands, they get weirded out because they're in grade 9. So I've got 2 kids doing it. I have yet to ever have a class that didn't have a kid that says, "Can we do this as an entire class?" And the answer to that, of course, is yes. That's my transition to the big circle. Right? Okay, everyone get to the big circle. They don't have blocks yet because that is just asking for trouble eventually. And so I hop into the circle a little closer to the camera. Can everyone reach a pinky to your neighbor within range? There we go. So I'm outside. There we go. Oh yeah, sorry. There we go. And then now you know the troublemaker in the class as well. So you got the one that really likes pain, and that's just an interesting fact to know about. And so you've got your first volunteer. Okay, so just so you can see way up north. So I've got little pennies made up. They have a symbol of a switch. And on the back side of it, there's a little cheat sheet for your kids that are high anxiety. So when you ask them what their job is, and if they panic, tell them, just read the back of your sign. And so we have found Heather, our switch.
It was you.
Sorry, switch.
That was fun. As part of the promotion as well. And so we've got our switch now. So her job, what did the switch do? It broke the circuit. They may not get quite that fancy at the beginning, but we have to talk about conductors and insulators. And so we've got a switch right here, and the switch broke the flow of something. It comes from chemistry, most likely, if you've done that first. And so we talk about protons and electrons. Where did protons stay? Your kids should say protons are found in the nucleus. Where are electrons found? They're outside the nucleus. What can conductors do? Their electrons can move through it. And so a switch is a break in a loop of conductor. So we have made the most simple circuit you can make. It's a complete loop of conductor. So we need to model what that is. So in a real classroom, now I give you the blocks. And let's say you guys represent a really, really big number of protons. What's bigger, a proton or electron? In theory, your kids know, hopefully they know, that protons are big, electrons, well, relatively speaking, protons are big, electrons are small. And so you, as a person, represent a large number of electrons. One electron can't do very much, but a bunch of electrons together can. And so if we do that, we call that really large group of electrons a coulomb. If you're feeling excited, you write a 6 with 18 zeros after it on the board and go, coulomb, big number. And for grade 9 electricity, that's all they need to know. A coulomb is just a really, really set big number of electrons that work like electrons. And so they pass one atom to another, and that's how we managed to get this circuit to set up. And so this represents a coulomb of electrons. They get to move. And so depending on what hour of the morning it is, I say, okay, get your block in your right hand, and you have to be close enough to your neighbor to reach them. Reach over the table there so we begin. So you should have an empty left hand and a full right hand. And I usually do a quick check to see how my kids are doing at like 9 in the morning because this doesn't always work well. Hey! And so you're going to pass your coulomb to your neighbor when I say 3, 2, 1, pass. Just once. Okay? Now bring it to your right hand. You should have your neighbor's coulomb at this point and ready to pass that on again. 3, 2, 1, pass. Pass. Oh, I thought we had an anticipator. Pass. Pass. Pass.
Oh my God! This is why I'm the switch.
Okay, so
Pausing?
okay, so here, there we go. So on film, what you may not have been able to catch was that kind of behind the screen, there was a person who had accumulated some extra coulombs of electrons because they had not yet. Some people were anticipating the word pass, and that always happens.
I was doing the good job of nodding.
So there was a buildup somewhere, and there was a section that didn't have enough. This is where I usually introduce terrible physics jokes that aren't original to me, but I treasure them anyhow. And so the person that has too many coulombs, we're going to pretend on camera right here. You've got 2. That's like that camera. And who we're going to pick on that's on camera? Over here. Hey! We've got 2 coulombs in your hand. That's very negative behavior. It's a terrible joke. If you're going to teach physics, it is destiny from the universe. It's divine, if that is your persuasion, to tell bad physics jokes. It's a rule. And if someone is missing their coulomb of electrons, are they missing them? Are you sure? Are you positive? I'm sorry if I just killed anyone in the Northwest. Okay, and so terrible physics jokes, optional, but in my world, essential. Good. Usually it's not the switch who drops the coulombs, because that is your natural transition to your next one. So we'll do that again. I don't know if you want to try to actually get the whole group in the shot for this one. Tweet if I'm not loud enough, but I'm usually pretty loud. Okay, 3, 2, 1, pass. 3, 2, 1, pass. 3, 2, 1, pass. 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 Yeah, there we go. Yes. Okay. Very negative behavior. You're missing one. Are you positive? There we go. Excellent. And so this person is the most noble part of our circuit, because this noble fuse was willing to lay down her life so the rest of us could live. We live indebtedly to you, O fuse. Okay. So fuses are an essential part of circuits. When coulombs go too fast, and we're eventually going to call the flow of coulombs current, or amperage will be the parallel idea that goes with that. If the amperage is too high, if there's too much current, our fuse, it has a job and it fails. And for a demo for this one, and this involves a bit of a safety talk, I'll be walking off camera for a second, and that's for a reason. I use a car battery for it, but the car battery does not exist on your desk. It doesn't exist out in the open classroom. And thankfully, I got to learn this lesson only a moderately hard way when a student picked up my small, the little batteries you use for like the little cars that kids drive, so they don't have to walk anymore and get exercise. Little motorcycles, those little batteries. And I had them on top of my desk, which I thought was kind of like sacred space enough that kids wouldn't, play on it. And a kid reached out, picked it up, inverted it over his head and said, "What's this?" And I went somewhere between apoplectic, speaking in tongues, screaming. I don't know what came out of my head, but like, "Ah!" And kids like, "What?" Right. And so you got a couple of significant dangers. One is the most concentrated sulfuric acid you would never, ever give to a student in a high school environment, or like until multi-year chemistry in university and under really strict supervision conditions. It's also got lead in it, so you don't want them like playing with the terminals and licking their fingers, because if they're doing that, the lead may not have an issue because it may be a pre-existing condition. But so I've gone off camera and I'm coming back on to show this is how I actually do it in class. And so that battery comes out and goes away and is under my control at all times. The kids don't get to touch it. Second piece to this is that it's a lead acid battery. If you try to short circuit little batteries, and you can do that, and they'll get warm, but it's not all that impressive. So what I have here is a decently long length of however big you think you need it for class. So what I do for the kids at this point is say, here, put your blocks in your pocket or put them on a local desk, that sort of thing. And so what we're going to do is we're going to short out a battery. A couple of rules for this. I always have my hands on the battery or on the controller here. So you invite your students to grab the wire. Here's my students, so you can grab the wire. You don't have to do this if you don't want to. This is an optional activity, but it is really cool. When you do this with kids, you got kids that don't listen to you at the best of times. You got kids that'll listen to you no matter what because you're the teacher. They're getting rare, but they are a thing. This is really fun. If you're not going to feel it, you're going to feel left out. Last call for people touching the wire. Okay. So again, basically it's going to get hot. I don't tell the kids that, but I say if at any point you feel uncomfortable, you should do that. And so we're going to come in here and, okay, I should have scraped my terminals before I got into here. There we go. Okay, so it's going to spark. This would melt crayons quite nicely. Okay, so There we go.
I just use like a small battery and a piece of
Oh,
bare
yeah.
wire.
Yeah.
And melted crayons in it. My parents found me and they're like, what are you doing?
There we go. So I should have polished my terminals before I got to here. But what people are currently feeling is that what okay. So if it feels uncomfortable, that also applies to you as the teacher. So there's a couple things to notice is that there's no clamp on the end of this wire. That's because if you clamp it on and it gets really, really hot and smoky, you're committed at that point to getting that off. Okay. So this gets really hot, and it's a good chance to show kids the importance of having our noble fuse, because a fuse will break. And if you want to demonstrate a fuse, you will need something really complicated like aluminum foil. Because it's thin, it's weak. I'll actually blow up the real fuse here for you in a second.
Can I throw a question?
Yeah, absolutely. You can always do that, by the way.
How is a breaker different from a fuse?
You don't have to throw the breaker away. And so as it gets hotter, it flicks the breaker over, makes a gap. And so you have to physically come in, put it back.
Okay.
So
because it just flips off. Like it flips off. So okay.
Okay, so bad teacher moment here. I should have scraped this in advance.
And you actually have a pro battery.
Yeah, we'll go to, and don't buy a new one. That's a really, really bad idea. They're expensive. Go to a shop and say, hey, you have batteries all the time going. Like this one I've done. Oh, and you also don't want to short out brand new batteries because that's like bad for the battery. So you're taking like an expensive new battery and doing that. There's no physics reason not to do that, I don't think. It's more just expensive. Okay, so if you want to short this out. Oh, cool.
Yeah.
Which is exactly what the kids will say. Okay. It's also important to manage your smoke production. It took a couple of years for me to not be called Smokey Robinson. That being said, if you haven't evacuated the school, you haven't done your job yet. Okay, one last thing. This is an actual fuse. This demonstration is always a quick one because it blows very efficiently. So this one, I forget what it's rated at. I think it's rated at 1 amp before it won't cook anymore. So here we go. So it's getting hot and woo, that melted. Okay, and so
Where'd you get the little fuse? That little thing.
This one I got.
You did a nice job on that one.
I realized that there's actually a couple wires that pull off this one that you're supposed to solder onto things. They were touching. That was a much higher amperage fuse than was actually inside. Anyway, well, you can get these.
Princess Auto?
Princess Auto would have buckets of them, online fuses. You just don't want something that can handle like 20 amps, right? Because then it's like, it'll look like a light bulb in that case. It just gets warm, really bright. Okay, and at this point, also just to emphasize this, I'm going off camera, but the battery is now going to disappear into my theoretical cupboards at school where kids can't see it or touch it.
Can you do that same demo without such a,
Big one.
with something smaller? That you have on?
Like your small battery you are.
A small motorcycle battery will. I'm still going to encourage you to get ones without plugs in them, which are a bit harder to get. But the ones with the little plugs that you can add more acid into, those plugs come out. And that's, well, from experience, a really, really poor idea for class. If it's a smaller battery, it's capable of less amperage. So you don't get the same oomph. You certainly can't do it with a dry cell like this. That's not going to work. It itself will get hot and your wires might get warm, but you're not going to be like big sparks kind of kill the fuse.
Because I've seen one where you just take a AA and the foil and you can start like a small fire with that.
Cool. Did not know that.
But then a fuse.
9 volts are even more impressive. There's a lot of fun videos where kids have like gone to recycling depots, got a whole bunch of 9 volts that are now like 5.5 volts because they're dead, and just done a click, 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 and done arc welding with them. I'm not saying that's a safe thing. That is not a STAO sanction. There are YouTube videos that exist in the world. But speaking of good things that are at STAO, instead of the energy ball that you got to see right here, which is kind of cool, they also have the Spangler version. So STAO now is able to sell a lot of Steve Spangler stuff. And so if you touch either end of this, it does the same thing. There's a small transistor that feels the current going through, a very, very, very small current going through you. You aren't running this. It feels that you are more conductive than air. And they're the $12 tax in. Probably the best money I've spent for professional science toys that gets kids involved. Okay, so we're back to actually being in class again. So we got a switch, we've got blocks, we've done passing. We have a noble fuse who laid down her life so that the rest of us could do well.
Sorry, I'm just buying negative big.
And we have an extra block. So someone might be missing theirs. You missing yours?
Matt says volume's coming through loud and clear, and thanks for the attention.
No worries. Okay, John, you try not to have it too obvious what we're going to do next, but I have them stacked up in the right order usually. So we got a whole bunch of electrons. And the key with this is a lot of vocabulary that is new for the kids, that goes with new concepts. And that vocabulary development requires like tons and tons and tons of scaffolding and repetition. And so what do those represent? Electrons, how many electrons?
Coulombs, so a big number.
Kids never are that good. But you're an awesome kid. I like having you in the class, right? They represent electrons. How many electrons? That big number you wrote on the board. What do we call that big number we wrote on the board? A coulomb. Excellent. So you guys are all wires. What's your job?
Pass coulomb.
Pass coulombs. What's your job?
It's too fast, I break the circuit.
Fantastic. What's your job?
I break the flow of coulombs by making a gap in the circuit. Am I gonna like step out or what am I
We'll get you working in a second. We actually have to get a few components that would actually allow you to control them before we get you to do it. But we will be bringing you in shortly. So why on earth would a whole bunch of electrons, these coulombs of electrons, again, repeating yourself, why would they want to go through a circuit? What gives them that energy in the first place? Batteries. And so at this point, again, I don't know my kids in my classroom. Who's the really crazy energetic one in this classroom? Excellent. Later on, we're going to move you just so we can kind of get some distance between components, and so you don't get nominated for anything else by other people's bad behavior. So batteries. This is kind of appropriate because we are going to have a battery that's going to show giving the coulombs energy by lifting them. And apparently, I'm assuming that you're capable of some elevation here. So what gives batteries energy in the first place? What gives you energy in the first place this morning? Food. Coffee. There we go. Teach grade 9s. Hopefully not too many of them are caffeinated. This is one of my favorite demos of all time because I usually start off with the kids. I'm like, rust, aluminum foil. If you get a really, really loud sound on this thing, it does hurt your speakers. Cool. There's no way you could possibly replicate this experiment because rust and aluminum foil are incredibly difficult substances to find in our society around us. And I wind up and I screw that up. There we go. That's a start. That wasn't a good one. Good rusty spot here. That's a bit louder. Sometimes it's worth it, depending on how strung your school is about things, to let people know there'll be loud bangs going off in class and smells of kind of chemically nature. And so, and then the kids are going to want to do this all lunchtime. So, this is called a thermite reaction. You can relate it back to chemistry about how much things like to react, chemical changes, that sort of thing. That's a pretty decent one. And so, it's also a chance for me to talk a little bit about environmental connections. It takes me 1 minute, but I say, aluminum comes from an ore called bauxite, and Canada has hardly any. It develops in tropical countries under really high, warm, wet conditions. So we import aluminum ore from places like Venezuela, and we have to deforest rainforests to do it. Then they put them in big boats and they send them all the way up to St. Lawrence because they need a country that's got a lot of electricity to do it. And so we dam rivers up in Quebec's high north, which destroys a lot of habitat. Go to Google Earth and see what northern Quebec looks like underwater. And so when you choose and you complain as kids, and legitimately that we are messing up the universe and people should do something about this, make sure you're recycling, because that amount of energy that comes from just this amount of aluminum, not a good one, That's better. So that little piece of aluminum right there that just came out, one foil thick, and less than the size of your baby pinky, that's the amount of energy that came out by reversing that process. So by recycling one aluminum can, and by extension, a lot of your other recyclables as well, you actually make a difference in the world if we do that as a society. So recycling is good.
So can you repeat the connection, the original curriculum connection to the energy that we create?
So where does the battery get its energy from? Where do you get it from? Food. Where does the battery get it from? Chemical energy stored. This is chemical energy. Now, it's going to be really hard to kind of show electrical energy because really we're pushing a bunch of electrons together. They don't like each other. There's repulsion because like charges repel. It's really hard to kind of show. If we had like a bunch of springs, that could be kind of fun, but that sounds like chaos in a classroom. So what we're going to do is we're going to represent that electrical energy, that potential energy you've given it, by using a different form that kids are fairly familiar with. Cameras is a bit tricky, but so the nice thing about these big, and now sold in a number of different science supplies stores. Flynn for sure had some at the conference on Thursday, I think. I know they sell them, and there's others as well. You're looking for thermite demonstration. That's the name of the reaction between aluminum and iron oxide. So to demonstrate energy, I lift up ideally a steel iron ball like this, and I drop it a bit, and it sounds pretty impressive on the desk. And like, so what does this represent? More energy. And you do this, and the kids get really excited. You're like, just kidding. I used to teach on the first floor for a bunch of years, and like a lot of banging sound. You're like, elephants again. So I got sent up to, I got the corner office now. And so I don't deal with that as much, but you want to be considered for people below you. So yes, that represents energy. So our battery right here is going to be giving, what are these called again? Electrons, a big group of electrons. What is that big group of electrons called? A coulomb of electrons. It's a good thing to write that on the board for the kids because it's French and they're like C-O-L-U-M maybe? No, it's C-O-U-L-O-M-B, coulomb. Just like it sounds. And so our battery is going to give energy to the coulomb of electrons. And specifically, you're going to, what are the units on a battery? When you read a battery, what are the units on it? What on earth is a volt? Potential energy. They will not say that. But it's great, though. And you get silence. It sounds like the power of the battery, battery strength. And those, you can work with that. Okay? And so it's the ability of a battery to give energy per coulomb. Oh boy, what are the units for energy? Joules. You may get that one. Probably not. Then you say, cool, awesome job, a joule. What's a joule? A unit of energy. Okay, well, how much energy is that?
Is it one freezing temperature of 1 gram of water by 1 degree Celsius or something?
That's going to be 4.186 kilojoules per.
Sure.
So no, it's going to take a number of joules to do that, though. Right, so the one thing that's helpful for this model is that these little blocks, okay, and you don't have to use wooden blocks, but it's handy to have uniform things to be passing around. People have done it with tennis balls in the past. I would exhort you not to arm your class with 25 projectiles of a spherical nature. And for the record, if you teach grade 9, these are spheres, not balls. They are spheres. Just for classroom management, you have grade 9s there. Okay, and so if they're working with these wooden blocks and they drop them, when they drop them, not yet, when they drop them, they go there. If you have a bunch of spheres with you, you've got kids doing like cross country, cross classroom, like it's like, oh my goodness, they're everywhere. Good. This, by the way, is going to take about twice as long. What we're doing here is what you'd actually do in the classroom, because in case you hadn't noticed, I'm hopping back and forth between you being students and you being teachers. Good. And so you're going to give 1 joule of energy to this coulomb. And this weighs about 100 grams. Okay? And so if you raise 100 grams, which is approximately a Newton of force under Earth's gravitational field, and you raise it about 1 meter, then it does not matter if it's 1.03 meters or not, about that far, that represent about a joule of energy. And until I'd actually done this demo, I actually had never thought, like, I got calories in my head and kind of like a chocolate bar and kilocalories. Had never really thought about what a joule was until that moment. And so it's an actually decently concrete measure. Like that's a real amount of energy. It's a joule.
How many joules in a calorie?
A lot.
Oh.
Google. And is that a kilocalorie or a calorie, right? Anyway, so you're going to be raising the coulombs up to a higher level. Excellent, because that's going to be a high energy coulomb. And our wires here, it's going to be a hard effort to follow, but you're going to have to, you know, you be nice, you be nice. Right, so your coulomb's going to have to come at a high energy level. Excellent, 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 excellent. Now the trick is that if it comes back to the battery and nothing uses the energy, you all do, and we got a really, really, really hot circuit. So something's got to use up that energy. And so I then asked in the class, who's got the best dance moves? Who's got the best dance moves in this class? This is when you make sure you promote someone else. So there you go. Well right. Because if you don't promote someone else, you get promoted. So you got to make sure that you, the person that you promote in class is like reasonably stable on their feet. So basically, I asked, you know, hey, if it was the 70s, could you do that? Could you do it more than once?
More than once?
Yes.
Yes.
We'll find out. Excellent. And so our coulombs are going to come from high energy, and our light bulb, its job is to take energy and to release it into other forms. And you're going to take that coulomb and you're going to pass it off at a low level down here. And you're a switch, you're going to pass it at a low level as well. And low, 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 low. Everyone up to here is going to be low. Then it gets energy here, and then it's going to drop down. And every time you do it, you do one spin. 3, 2, 1, pass. Good. 3, 2, 1, pass. No, hold on. You're messing up my model because our light bulb's supposed to be the slow one here. Oh my goodness. Okay.
I'm passing it, right?
Everyone have it in your right hand. That way, there we go. Okay. Right hand, right hand, right hand, right hand.
You're gonna lift this and pass it after you pass that.
Pass it high or low?
High.
You take low energy coulombs, and you give them energy, and they leave at a high energy level.
Okay.
Yeah.
Take it low, and then you have to elevate it.
He's the only one that takes it low.
Okay. 3, 2, 1, pass. 3, 2, 1, pass. 3, 2, 1, pass. This is a fantastic light bulb, by the way. Say pass. Who keeps passing? Who keeps passing? I did not say pass. We have disobedient parts of the circuit here. Oh my goodness, we've got craziness. Okay. Oh, by the way, you will have to do this many, many times. When I say the P word, which I didn't just say, but when I say the word that starts with P, you will then transfer it to your neighbor. I did not say the P word. So, okay, good. Normally what happens there is your light bulb, while trying to figure out dance moves, is slower than the rest of you. So you're going to imagine that happened because we have one fantastic light bulb right here that can like cut a rug. So, very good.
I know how to promote my light.
Okay, so our light bulb there, normally what happens in this will be the thing that slows down the flow of coulombs. Any questions about the models so far? That's what you should have seen, because that's what normally happens.
I have a question.
Yes.
I noticed that the negative and positive terminals on this side don't we usually come
I made a corrected set of these. The Blackline Masters that I have stuck in the resource section, yes, have been corrected for that. My kids have never noticed that.
Actually, I do have a question about that too.
Yes.
So, it's right
Technically,
now.
that should be.
It should be this way.
Or we should be going the other way around.
Positive and negative.
Yeah.
Okay, so my only question about that is just, this is always for me because I think about it. And so electrons flow towards a positive.
Yeah, so I do have the battery backwards here for what I'm doing right here.
Oh, okay, so it is positive on this side, they're going to the positive?
Yes.
Oh, okay, sorry, I thought it was, but on some circuits I've seen that it's
By
actually.
engineers.
Yes.
Engineers talk about a positive
Yes.
pole, and that's a historical anomaly because they understood electrical function before they understood how it worked. And as per usual, engineers figured out how to make something work, made a lot of money, and then let the scientists figure out why it worked.
Yeah. Still use it today.
And still use it today, historically.
Yes. All the mechanics, electricians, they use that.
Yeah, and then in grade 12 physics, you were forced to make terrible decisions. Are you prepping people for physics or engineering? Because all your engineers and most of your grade 12 physics textbooks will talk about positive current flow
Yes.
to prep kids to become engineers, which essentially is the same thing as prepping them to be wrong. But
Because even in chemistry, we would immediately go, well, how could that be? Why would an electron go towards a negative charge? It would never do that.
and there's the tension that will eternally exist until engineers admit they're wrong.
Okay, well, sit tight.
So when the engineers admit that they're wrong, we can stop having this conversation. Our great-great-grandchildren will have this conversation. So the next piece you need to promote is an ammeter, which I do by saying, hey, who can count by whole numbers first thing in the morning? Again, I teach like first thing in the morning, first grade. So yeah, there you go. You know the rules are. You promote it, you get promoted. So every time a coulomb comes through you, we need you to count. Okay, you got this? Okay, you should all have your coulombs in the correct positions energetically. So where should your coulombs be in terms of energy? You're high, you're high, you're high, you're high, you're high. Low over here. Low, low, low. Low, low, low. There we go. Okay, 3, 2, 1, pass. 3, 2, 1, pass. 3, 2, 1, pass. Okay, and be nice to your light bulb. And like this is a real consideration if you have a classroom of kids and you got a kid that's gone around 13 times. Do you want first aid first thing in the morning? No, you want your kids conscious and not bleeding on your floor. It is a pain to clean. Right. So be nice to your light bulb. So how many coulombs did you say passed through you? 3. How many did our battery pass during that time? Any guesses? If you had to guess. Probably 3. How many would you think were passed by this part of the circuit? How about over here? When we have an ammeter in a simple circuit, if we put you here, 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 you should read the same amperage every single time. Because the current in a simple circuit does not change. Everyone has to pass at the same rate. What happens if you guys don't pass at the same rate? I got 2, right? I got 9. And in grade 9, we say that's a physical impossibility. When you add capacitors to circuits later on, it's a thing, but capacitors do not exist in grade 9 chemistry or physics or anything like that. They're not a thing. Good. And so we have an ammeter. And so what do ammeters do? They count the number of coulombs that travel through them. And here's the last little piece, an amp. Okay, and the kids have probably heard that in some sort of battery commercial for Canadian Tire, 40 cold cranking amps. That would be an impressive battery. Anyway, something with amperage they've probably heard of. They may say, oh, amps. You're like, it's probably a speaker that stands for amplification. But yes, they take a lot of current. That's good. And so you count the number of coulombs that travel through you specifically per second. And so coulomb per second is an amp. So notice that we have taken care of a lot of vocabulary for kids so far. They know what a volt is and an amp is. We do not do ohms quite yet because that will come naturally later. The last thing we need to figure out, so we know that light bulbs are going to take the energy. We need to make someone a voltmeter. You got a couple of options. You can promote yourself as like the judgmental one in the center, or you manage to get come forward. We present to you the rugged individualist, set apart from the circuit, who stands in judgment of all of you. We steal your coulomb, and we promote you to voltmeter. Voltmeters have a very important job. First of all, they're not allowed to be part of the circuit. They do not pass coulombs. In regular physics speak, as teachers, they have crazy high resistance, and so if you put them as part of the loop, it's just like they refuse to pass coulombs. Ammeters, notice, have to be a part of the group. Otherwise, they can't. If it doesn't go through them, they can't count it. So kids are already getting a visual on all of your symbols. They have an idea of all your functions. They've got an idea of all of your vocabulary, except for ohms and watts yet. And so we now have a voltmeter. They've got a visual. The voltmeter is in this mysterious box in the kit. You get to be the voltmeter. You're the voltmeter. You are not part of the circuit. They remember you've been pulled out. And so your job is to go and look for energy differences. Let's see. So everyone get your coulombs in the right position.
I got the 2 and then.
Let's see. Okay. So where's the low energy section of the circuit? That's
I
right
started
here.
right here.
Where does it change? Where do we find changes here? Ah, and so our battery, and sometimes I'll grab a meter, sometimes I'll grab a meter stick and say, like, there we go, 1 joule of energy per, yeah, so 1 joule per coulomb. Oh, excellent. Is there any energy difference here? And that's the fun part about bringing the voltmeter in. Like, sometimes I take it really seriously and I'm like,
wow.
too hot, too low, you must be exactly the same. Right? They become like the Voltmeister or something like that yells at kids.
Yeah.
It's fun. Good. And so you've got all the different components doing things. And then we look at the light bulb over here and say, well, where does it drop down?
It's when he moves, goes down there, right?
Excellent. So we have a drop right across our light bulb right here. How do those amounts compare? The raise here versus the drop here.
Should be the same.
Yes, perfect.
Yeah.
And so we've learned a few things, that fuses don't use energy, ammeters don't use energy from the circuit, our switch doesn't use energy from the circuit, so light bulbs, they have a job to use the energy from the battery. That electrical potential energy becomes light, sound, motion, all sorts of fun things, heat. You can also, if you like getting your light bulb really going, you're like, who's hot in here? Hey, look, our light bulb off to the side here is hot because they're spinning. If you haven't seen him spin yet, we have an excellent light bulb off screen here who every time it gets passed has to do a spin. And so they get very warm in the process. Good, and so they've seen all your different parts. The only thing we haven't played with yet is our switch. For functionality, I try not to put my switch and my battery right beside each other. I try to make sure there's always just a wire, just a passer between them. And so we're gonna pop you, just kind of 2 people down and shift you guys to fill the spot. Good. And so in terms of functionality on our switch, what I get my switch to do is I say, well, at some point, before the light bulb passes out, and this is always a fun kid dynamic where they're like, pass that. Well, I didn't actually say that. Transfer. So you have to kind of like make sure that your switch is nice to your light bulb so they don't end up bleeding on your floor. So your switch, at some point, but I'm just going to keep saying pass, you're just going to simply turn sideways and look very threatening and not allow any coulombs to go through you. How many coulombs are you allowed to have? Right, because you're a coulomb of protons, you're only allowed 1 coulomb of electrons. How many are you allowed? 1. You? You, 1. So if you have 2 coulombs of electrons in your hands, terrible things will happen. Okay? 3, 2, 1, pass. 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 3, 2, oh,
I don't want it to do.
that was fun.
Any others?
Okay. The other thing you can do with your voltmeters, you can promote them to do other fun things like, hey, I know you normally look for energy levels, but I need you to do some bonus things that don't happen in physics. Bust the extra coulombs. Right? And then we like say very serious things like, young man, expect better from you. I'm calling your parents. No, a very scary thing. I'm inviting your parents for lunch. Even scarier threats. Who's actually missing their coulomb? There we go. This will take you at least 3 times for you kids to understand that the switch means business, right? Now, if you have creative wires, if you didn't see it on screen, basically the wire forced it upon our, reticent switch that didn't want to take it and basically said, you got this! Oh, coulomb assault. That can happen. But these are all teachable moments. And so we're like, okay, well, that didn't work well. How you doing? Checking on your light bulb.
I'm hot.
Naturally. Are you spun?
I don't know what that means.
Have you gotten many times? We'll go for that definition. Yeah. Okay. Let's try that again. 3, 2, 1, pass. 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 3, 2, 1, pass.
Where we go?
Okay. So. Okay. So remember, this is a group of teachers that we're working with here. That's twice.
Does it actually work that the electricity piles up at the switch?
No,
or does it all
no,
stop?
that doesn't happen. So that's usually when I have to, threaten, like, you do realize that if this happens again, there'll be a meteor strike that comes from the heavens that will pour down fire from heaven upon us and burn us all to a crisp, or something ridiculously over the top. And there we go. What we see is that the learning spreads from here to here, and then eventually we'll get everyone to notice that, wait a second, I got to pay attention to the switch, and which is where we're going with you. So let's see if we can do it on average the same number of times as a high school grade 9 class. And if your voltmeter gets really bored, you can promote them to the same pass as well, which is fun. Want to try it?
Sure.
Okay. Okay, pass. 1, pass. 2, pass. 3, pass. 4, pass. 5, pass. 6, pass.
So, 7.5.
Yeah, okay.
I haven't taken fast enough.
Because how did they make it? And none.
There's just one that.
What would the voltmeter do, actually?
Depends on how you want to promote your voltmeter to chastise the youngins. Okay. So that wasn't actually an issue of people not paying attention to the switch. What ended up happening was that was a cascade of drop. If you have a drop block, then you kind of have to let the blocks get picked up in the process, kind of keep going. Oops! Apparently my switch went. Cool.
Maybe
I've got tape somewhere.
It was stapled and stapled.
Ah, perfect. Your switch, you'll remember that.
Okay.
Good. So that's our model so far. So usually it'll take 3 or 4 times of slowly working your way down the Boration line of now you passed without waiting for like you heard the word pass, but you didn't pay attention to our switch. Are you allowed to have 2? No. Should you have taken 1 if you couldn't give 1? No. And so it's gonna. Like I've had times where we've done this 6 or 7 times. You're like, well, they got to learn this adventure eventually. One of the other fun things is that I often will start with my switch here between the battery and the light bulb, because the kids' misconception is, well, look, right now the battery can send coulombs to the light bulb, therefore you can't control it, right? And so you have to do this model and do it a few times. I'm not sure if that was visible off camera. And so currently we've got a switch that is after the loop in our circuit here. And so our battery can pass to the light bulbs, and kids' misconception is that so long as there's no switch in this section, you can still pass. And so in a regular classroom environment, I would then do that again. It's worth the time because the misconceptions are real and they need to be broken.
So it's a good idea to have the switch outside of the wire between the light bulb and the battery there?
As long as you mean still within the simple circuit. Okay. Yeah, so do the here and do there, absolutely. Right. Good. Any questions? Because we're about to move to the next goal.
So with the voltmeter, would you get them to measure like within the lines, there's no difference?
Yes, so no difference. So full volt drop.
They can only measure at the light bulb and at the battery.
Well, they can measure anywhere they want. You strip off a wire halfway through, you can test there if you want.
Mm-hmm.
Shouldn't, but you can. All right, voltmeters can test anywhere.
Mm-hmm.
So
right here.
There we go. Any questions about the model, or even just about physics, about our grade 9 electricity simple circuit model so far, either teaching or how it works in real life?
Do you get into resistor at all, or does that?
So remember when I said that our light bulb was supposed to slow things down?
Mm-hmm.
That's usually when you introduce the idea that the job of the light bulb is to take the energy from the battery and to release it into other forms. Where does it get hot? Here, because you have energy transfers. Who slowed us down? Our light bulb. Except
Should you turn it slower in order to show?
Well, almost always. Like I've never actually had this happen in class.
Because it's a really good light bulb.
Where a light bulb is literally so quick to be able to do boom, 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 again and again and again. And we only had one time where you struggled because of a handoff that went funny, and then you were doing like crazy things, and then you actually had to slow down. But besides that, this should be, in principle, easier than Magnifico over here. Okay. Yeah, so that's where we talk about resistors. Who's slowing us down? You're slowing us down. And then we're going to get to adding 2 light bulbs, then like 3 classes from now after we've done the paperwork, the theory, the building with circuits. Now we move to the next model.
Okay, that was what I was gonna ask. With the 2 light bulb model, you only do half as much, right?
Yes, that's what's going to happen.
Type of thing. And then do you ever do this with parallel?
Absolutely.
So yeah, I've never seen the parallel one done before.
It'll be fun. Okay, but before we move to that, so what we do normally, let's go back to class, we collect all the blocks, collect all the pennies, you sit the kids down, you do and this is a review sheet. There's a series of blanks that we have in the Blackline Masters, and you simply say, like it says, what's the function of a battery? And so in class, I'm still learning names at this point, and so I'm back to talking to this new student that I've just learned and said, so what was your job today in class?
Energizing the food rooms.
Fantastic. And whatever the kids give you, right, and this is beautiful because I even had, at our school, we do applied academic mixes. We don't split until grade 11, which is kind of an exciting thing. But it's been a cool thing with this because often when we test kids, we often test for what they don't know. But testing for what they do know is more exciting. And so even if you have no words, what do you have? What was your job? Right? Even my kids who have struggled a lot academically, who are not going to be the kids that are going to rock out a 90 with all the nice little theoretical words, can still tell me, what was your job? Fantastic. You know what a battery's job is. Now let's develop that. What's that? A block. Fantastic. And you will get that answer sometimes. What does that block represent? We're scaffolded, right?
Electron?
They represent an electron or a bunch of electrons? A whole bunch of electrons. See how that big number on the board? This is what happens. This is good because you have students who genuinely struggle and will sometimes say block, right? This model doesn't work well when you get a group of physicists that are like, well, that'd be 6.28 and 10 to the 18. Would you look at an electron volts? They're like, thank you for your degree in physics. That's unusual in my grade 9 class. Good. And so what was your job? So you were doing something to that coulomb of electrons.
Bringing it high.
Go to high. Good. What does that change represent? What were you giving those coulombs? Energy, right? And then we say, well, when we're giving a joule of energy to a coulomb, what is a joule per coulomb? What's that unit called? A joule? Or what are batteries labeled as? A blank.
You're asking me?
Yeah.
Sure.
Or the class, right?
Sure, yeah.
It's the volts, right? And so you've got a repetition both here. Now we're sitting in a classroom, and you get to reinforce what you've just done here. And you get to work with the kids, especially, you notice that the kids that have got the pennies usually are the high energy kids that you have to bring into class anyhow, because their classmates have generally nominated them, right? Yeah, and again, usual classroom stuff, if someone has meanly nominated someone, right? And they seem to be particularly anxious or weak, you can ask someone else, what was the voltmeter's job? You promoted her. What was her job?
Make sure
Potentials. And sometimes kids may say that, but they'll repeat the vocabulary you've given to them. Yeah, and so if you want to introduce potential energy eventually, good. Were they inside the circuit or outside the circuit? Perfect. Notice we're seated in desks right now, right? So you're reinforcing what they physically saw. And hey, you promoted her. What was an ammeter's job?
She's counting the coulomb, but after every second.
Wow, first time. That's unusual, right? You may get this. What's your job? This. You can work with that. That is knowledge that has been transferred. Okay, and so they pass what? What are those things called? They are called coulombs. What are they coulombs of? Electrons. You can reinforce that they're negative, that they move from negative to positive, that engineers are wrong. These are important lessons for kids. So when we have gotten down to the list of, what was your job?
I was losing energy.
Good. So did that energy just disappear or did it take another form?
That did take another form of converted energy. Yeah.
Fantastic. And so as a light bulb, what types of energy do you think that would take?
Well, probably light and probably heat.
Fantastic. Your easy bake oven. Don't put LEDs in your easy bake oven. You get easy bake nothing dough, right? Fantastic. So you can work through everyone's job, from our fuse and even to our wires. There's a question about how about insulators? What's their job? Well, none of you were insulators. If only there was something that told me about the importance of what an insulator does and avoiding short circuits. And so your kids already have a strong foundation. This rarely takes more than half an hour once you get the kids, in place and going. We've done a lot of additional teacher speak on the side, but I'm typically at about half an hour. If I've got a applied heavy class, sometimes it's 40 minutes. And it depends a little bit on how much homework you've done on prepping the kids to settle. You guys are the least fidgety group of adults I've ever had this happen with. This is normal activity. Flippity, 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 flippity. They're bringing out kids, right? Like they're like, what would I do, right? That went better than I expected. And so, just in terms of a management thing, I say, like, if we're passing and you drop, no harm, no foul. Like, you're doing what you're supposed to. Like, you're doing your best. Unless I see you, like, flinging at your friend's head. But it's really disruptive if you have 12 kids dropping a block constantly. And so I say, while we're discussing things, you got options. You can hold it, you can pocket it, and you can fidget. But here's the rules. If this is clattery when I'm talking, you owe me a minute at lunch. Your call, right? So you got choices. You choose your choices, but not your consequences. You need to find your own management style for your kids, but you need to have this under control. This not in control is not a good idea. You've armed the young'uns with lots of fun projectiles. Shall we add a light bulb if there's no other questions?
This is something you do day one.
Day one, yes. Sometimes you can do statics for a day. I light end the statics for, like, here's some really cool applications of static electricity. Stay in your car during lightning storms. This is how we clean the air that you'll be learning about next year in climate. This is how we paint cars. This is how to have fun with friends at the farm. That sort of thing. That's electric fences. Anyway. I do a day of applications usually, but this is where I get, because I want the kids to build me a small cardboard house with switches and light bulbs and stuff at the end. So that's what I do. Okay, so we have unofficially gone back to class. We've filled in some notes. We've played with a bucket of equipment. We'll talk more about this bucket of equipment later. But we come back out to the hall. This is either 2 or 3 days of work, depending on how long your periods are. You've done the same sort of stuff. I always keep my battery the same to emphasize that we have the same 1-volt battery. Everyone else, I generally switch up a little bit, but for the sake of time, you guys are stuck. So I need one more bright person. Who are we nominating? You feel comfortable enough doing a spin?
Okay.
There we go. So you are like, ta-da. Okay, so when you do this model, there's a couple of options. Now, first of all, they've actually built, and I always have more than one light bulb in the kit. There's kids who are going to get done that lab in lightning time, that just look at it and go, I'm spatially smart, I can do this. Not always the academic kids either. Sometimes the applied kids get on fire, and they're beautiful moments when they explain to the applied kids how to actually put something together. Book smart kid. So those can be fun moments. There's a moment, and your teaching style has to dictate it, whether you're going to explain how this is going to work, or if you're going to watch Chaos teach a little bit. Not sure if you've read me quite well enough yet, but my style is Chaos is wonderful when controlled. And so I've got my voltmeter outside of the loop, no block for a voltmeter. The rest of you have a block. Before I've gotten kids out into the classroom, we reviewed everyone's job. We reviewed what this is. We reviewed rules of classroom. And then, do we have the same batteries before? Excellent. And at this point, I make no clarification, but this happens. You got kids who are like, whoa, we got changes. What are we supposed to do? Aren't you going to tell us exactly what to do? And you got other kids who are like oblivious to the fact that even though you've said, we're going to change the circuit and make another light bulb. And in spite of some of these kids having actually, like in the previous lab, done series circuits already, don't care what's going on. They're like, I'm not a light bulb, not my problem. I just pass coulombs.
Question.
Of course.
So I have to take my column here, my electrons, and then turn.
Yes. Okay. Is that the only question that we have so far? No? Okay, good move. 3, 2, 1, pass. 3, 2, 1, pass. Okay. Okay, so we're going to stop it right there. And so now we get our voltmeter to do some hooking here. We had the same batteries last time.
Yeah.
Right. So we want to make sure we emphasize this early on. Right? You're excellent battery. Like, do you feel any less energetic than yesterday? I think fantastic. We're completely charged 1 volt battery. Any change in energy over here? Excellent. How about here?
Yes. Well, she's got two. No.
Okay, and a couple of important things is that voltmeters do not measure the number of coulombs. They only measure energy differences in coulombs. Right? And so the eternal battle in science is matter, energy. Separate things. Coulombs are matter. Joules of energy are energy. So what the matter is doing is energetic. What it is matter.
So this is different.
If that's 1 volt, what do we got over there?
It looks like half.
It's a half.
Yeah.
Okay, that never happens, by the way, right? Because you would have seen last time our light bulb, take it at a high level, drop it to a low level.
Yeah.
What usually happens is somewhere in here, magic happens, right? Or it just happens at low level, you're like, whatever, right? And around we go. And so you try your voltmeter around and we kind of go, I'm sorry, what's your job? Pass coulombs, and yes, and okay, very, very talented. This has never happened in class situation, right? You're at like half a volt in grade 9 land, right? You'll be down here for sure. Or the light bulb passes at full energy level and spins anyhow. It's like, yeah, I got this. I'm releasing energy and not taking any. Patent this, right? And so those are the things that you're going to run into. So you run your voltmeter around and say, well, that's kind of weird. So somewhere someone makes up energy, whether it be here or whether it be here. Usually by this point, it's not a big deal. It's just same old low pass right here, which then gives us the moment of saying, well, we changed something. So what's the difference? Okay. I'm not sure if you can see this on feed. We actually have 2 light bulbs here now. There we go. There's the 2 light bulbs. My apologies. And so we've got 2 light bulbs, and the issue is that we were coming at high energy, and these guys did a great job. They dropped a half, and our second light bulb dropped at the other half, and that's what happens in reality. If our battery doesn't change, then they have to share. Usually you've got kids in the class who are kind of keen, who have actually worked with the circuit stuff, and they know that you can get 2 bulbs to light up. So first of all, this is a thing. It's possible. It's a physical reality. The second piece is that if they're going to have lit up 2, it's almost always a series circuit, and so it's down to half. And so what we have here is we've got a light bulb and another light bulb. They share the energy. Inevitably, you have to say, well, how's this going to work? And you'll eventually, as a class, agree that you're going to do a half each. Because the other solution to this, get a better battery. Come on. If you're gonna have 2 light bulbs as part of your family, you're gonna get another job, right? Come on, let's feed the bulbs, right? So we could solve this problem by having a 2 volt battery, and then you guys can each have a volt, right? You're the first human I've ever had in grade 9 that could actually pull this stunt off. That's impressive. But we're gonna work on the assumption that your battery was great in the first place, and we don't need to change it. It's fabulous. And so it's going to be a half volt here, a half volt there, and they only get to spin halfway. While they're figuring out how does that work with a block, before they figure it out, you say 3, 2, 1, pass.
What is she?
Just take a block out. That's all. Put a block out. There you go, like a 90.
And and you go 3, 2, 1, pass.
The
confusion is normal, and it's what you need. Because what you need is confusion so that they aren't such great light bulbs. Right? You need this, because what happens is they take it at a high energy level, they pass it to their hand, they spin halfway and go, wait, didn't I just see you? Yeah. And then so they take it, they pass it, they bring it around, they look, they pass it back, they give it. They take it, they pass it to themselves, they look at you, they pass it back, they give it. It takes them about 7 or 8 turns to go, wait, I just take it and hand it. Whoa, that's way easier. So you take this moment of chaos and you say, look, right, boy, this is sure slowing things down, eh? So, and usually, who would I ask about the slowing down of the flow of coulombs in the circuit? Nope, voltmeters don't look at the flow of coulombs. Light bulbs experience it, but the ammeter is the one that measures it, right? And so this is your chance to bring in potentially the high action kids in the class. It's going as fast as last time, or does it look slower to you? That looks a little slower to us, eh? Good, and so we see that it slows down. That being said, even though it's slowing down, how many do you think we passed during that time?
In the classroom?
Yes. Two. How many do you think our battery passed? How about that light bulb? So far, there's been no significant change in amperage between the simple circuit and a series circuit. The only thing that's changed is that while the amperage is the same everywhere, the circuit has gotten less. You have to grab this model on the early stages while there's confusion, because this model, once you are both talented and have figured out whoa, that's easy, will not slow this down very much anymore. And then the model starts to break down because you're like, whoa. So apparently bulbs in series makes it easier, which it doesn't. So catch it early while there's chaos. And if you need to promote a kid that you're like, probably is not going to do great with the handoff, you do what you got to do. Okay? So confusion is fantastic for this model. It's really good because it gets the slowing down process. The fuse, generally I don't reintroduce the fuse for the later lessons because we're going to try not to kill you along the way, ideally at least. We'll reintroduce you at the very last part of parallel circuits where we say, remember a fuse, where would it be a good spot? But that's going to be like 4 classes from now. Good. Then you go and, so you've incorporated your ammeter, and you're still a switch, excellent. Okay, and so we'll do a couple of rounds of switch adventures, and we'll see if people remember the functions of switches. It's going to be the same answer, by the way, as last time, in theory. 3, 2, 1, pass. 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 3, 2, oh! And you will have to do it a couple of times. Oh, no, there.
Because
well done. Well done. There we go. So are you allowed to pass it if you don't get one? Right? It's been 3 days since you last saw us. How can you be expected to remember? Right? This is normal. And you will have to do it a couple of times until kids will finally get, and then you move your switch, and it'll happen a couple more times. And that's normal in this process. Okay? Any questions on switch function or bulb function so far? Ammeters, they count the same everywhere, but now they count a lower number per second. Okay, so our voltmeters already been incorporated. What was our battery? 1 volt, half a volt?
It's 1.
1 volt. And on a light bulb, how much energy was used? Yeah. Remember that thing of tidiness at the beginning doesn't happen. Your voltmeter, part of their job is going to be to come in and say, what? We had a full volt drop here, and then how dare you spin without energy? Or like, shouldn't you be down here, right, to get the same thing? And so the final thing we got to do is kill a light bulb. Not literally. They frown on that in all school board systems, right? And so sometimes in my classroom I'll have like a big rolly chair or like a hammock up on a block and tackle system. And so I go and kill a light bulb and say, I'm so sorry. You will be dearly missed. There was a terrible accident in the circuit and you've been broken, right? So now there's a gap right here. So can you pass over the gap? No. I'm an insulator, right? So we can't have any passing through here. So we have a, dearly beloved, we will miss your light bulb. Bright and shiny light. 3, 2, 1, pass. Did we manage to have people not pass for a change? We win! We win! No high voltage, no RC, right? And so if we have a light bulb that dies, what happens to our other light bulb? Did it spin? No, but it's good because that's going to be one of the other answers, right? Now, if you could pass, what would happen to our light bulb? Then it would get brighter because it would get the full volt. But if our light bulb here is a air gap now, can't pass, does this one burn out?
No.
It goes out. It's a picky thing that I care a bunch about in my class. You probably should in yours as well. This doesn't equate destruction. It just means inutility. Yeah, unemployment, right? Good. And so that's a function in series. Notice that one a little quicker, right? This takes less time. Going into real life will take more time now. It's going to take more time to do the lab because you have more places to stick an ammeter now. In real life, they're going to put an ammeter there, and they're going to put it between the bulbs, and they're going to put it right after the battery. They're going to move the switch around to a couple of different locations and see how it functions. And so this will go quicker as a model, and this will go slower in terms of then having to build circuits and do theory. This is your chance to introduce Christmas bulbs, the way things were terribly done when I was a child. Right? If one bulb burns out, you had to replace every single one until it worked. And if two bulbs burnt out, that meant that you had to replace the first one and replace every single bulb. And if that didn't work, then you put the other bulb back in the first one, replace the second bulb, and had to replace the rest of them. What actually happened is you threw the bulbs out and we just waited until parallel circuits were finally figured out for bulbs. Right? Any questions about series circuits, either the teaching model here or just how physics works?
Sorry, we're like almost 20 minutes over time.
Oh,
Can you just quickly go through what the parallel is, because there's another section.
Yes, thank you. You're already here in the middle. Can I get you to stand right here? Okay. Voltmeter, you can either be part of the circuit, or we'll just get you to be judgy later. But I do need to, can you take that off and just become part of the circuit right here? Thank you for the heads up. I really appreciate that. Can I get you to come in here like this and face me? So, other light bulb, can I get you to go over there? Can someone switch places? Or just kind of shuffle around? Well, this happened 2 days later.
Oh, okay.
So we're in class. We've done series circuit theory. We've done building. We're now in the hallway. We reviewed. You can say what's going to happen, or you let chaos happen. We're doing chaos. 3, 2, 1, pass.
I don't even know what we're passing.
Exactly. Stop. We're going to stop right now.
Okay.
Good. And so, who are the anxious people right now in the circuit? These places right here, right? Something's different from before. So to speed this up, we'll ask your kids, well, something's not working. The result is a big pile of blocks over here. There's a loss of blocks over here because you both passed and you can only give one, right? So where'd the extra one go? Where did it get fixed? That's the extra one? Okay. Does everyone have one block now? You have none? Who's got the two?
Someone has to.
Someone.
There's one here.
Yeah, but this.
Okay, we're gonna. Oh, that's right. Voltmeter didn't have one. Right? There we go. Okay, sorry. Okay, so what we talked to the class. How do we solve this? They usually say, "Can I rip the block in half?" I thought about putting Velcro between them. Then I thought of the sound of that many Velcro rips in the class and thought that's stupid. So what we had to get from them eventually is that you guys are going to do on pass. You guys are going to forget that the P word ever existed. You guys are now transfer at the back. So it's going to be pass, transfer, pass, transfer. What are you guys? Okay, you're conductors, you're both, right? So when I say pass, you got to do that. If I say transfer, you got to do that. If I say pass, what's your job? If I say transfer, that way, right? So if I say pass, where's it coming from? If I say transfer, that works. 3, 2, 1, pass. Your light bulb, yep. You do one spin. Transfer.
We still pass.
Pass. Transfer. Okay. We're going to stop there for the sake of time. Good. And so our light bulb here. Let's see. So did you take any energy? Okay, and this is where I would incorporate the voltmeter in. You guys take any energy or just wires, right? Yeah. And who do you have to share with? Yeah, full joule per coulomb. Good, so you get the full volt, right? So you do the whole turn, fantastic. And what are you doing back there? The same thing. Same thing. So for the first time, we've got no sharing of voltage. Right? Every branch gets the full battery's gift right here. What happened to our amperage? So we talked to our ammeter, we would say actually do some counting. You would have counted, I think we only actually did 2 each in that case. You counted 2 here, you counted 2 here, then we draw out a view that you did 4 over here, right? So amperage is changing in a parallel circuit. So it's the opposite of series. Amperage is splitting, voltage is staying the same. In series, your voltage was shared and the amperage stayed the same.
So do you tell them pass, transfer, pass, transfer?
Yep. Then we work our switch into it, right? And so our switch is blocking right here, and all it does is block the passes.
So
That will take about 8 times for that to actually figure out that the passes won't do anything and transfers will still work. That depends on how much you want to play with that one. So the switch can block here in this position, and we then ask the switch, well, where would you go to control our light bulb here? You couldn't do it from this position, so we have to move you somewhere after the branch here and before the branch here. So far, so good?
With the amperage would be half, and it should be a full when one branch is down.
Okay, so this is a model, and models are not perfect at predicting, which is why we actually do the lab.
Okay.
And so the one thing you have to get through to the kids eventually is that you do not determine amperage. Batteries don't determine amperage. It's what, like, that thing is capable of magnificent amperage. I'm pointing to a large car battery off screen. That's capable of magnificent amperage right here. But what's the amperage right now with nothing hooked up to it? 0. What was it when I hooked up a bare wire to it? Crazy, right? And so it's what you hook up to it that determines it. So then I say, well, what happens if we add a 3rd branch and a 4th branch? Well, you guys are all kind of like, this is easy. What are you guys doing if I'm doing pass, transfer, gimme, Benoit, like 18 different branches? You guys are going nuts. So where does our fuse need to go in the circuit? It needs to go right
here
at the panel. It needs to go right after the battery. That's the fuse's job, is to be on the high amperage section over here. Here, not as important.
So the guys that were on the corners here, when you said pass, he went that way, but when you said transfer, he went.
Yeah. And then over here, pass, transfer, pass, transfer. Okay. And so light bulbs get the full voltage. They're equally bright. They pass at a normal rate. The more that you put in, what happens if one dies? It's like the switch being here. Can you still work if this one dies? And so that's the blessing of parallel circuits. Everyone gets a full share. Which one will kill a battery quicker? Parallel or series?
Series.
Series will make that run out of energy quicker.
Yeah.
Lower amperage, same voltage. This does high amperage out of it.
Yeah.
So this one's going to make it die quicker, right? Because you got lots of bright bulbs, right? That one will have a bunch of really dim bulbs. And so we've sent our voltmeter through. You have the same battery. Wow, look at all the energy you're releasing. Look at all the energy you're releasing. Any questions? I don't want to hold people past their break. I'm very sorry that ran a bit later.
Just is this? Is there a video of this? Because I
Absolutely, yeah. And so I can actually see if we can get that live up on my computer.
TD physics?
Sorry, it just said 1 o'clock on it, so I thought it was.
Absolutely, and there's a bunch of people that are here for certificate programs, for stickers. And so some of them have already told me they have to leave, and absolutely, thank you for coming.
No, it's weird because his thing says 12 to 2. So some people think it's a 2-hour session, but some on another paper it says 12 to 1.
Yeah.
Hey, thank you for explaining why there's confusion. So we're going to return the block. We're going to do some more discussion of the model and stuff at this point. Thank you so much for coming. It's a Saturday, and I know that's a big sacrifice.
Do you have handouts at all for this, or?
Yeah. This is just kind of a reminder of what is available online. Because I find that if I go home and don't have something physical to look at. So this is just like the first series circuit teaching models. The first version of the Black Line Masters and the first version of the answer sheet. Can we get me back on that? People should watch that. When electrons move is small and that's been really
So is that where
I talk about firing electrons. So for the work away, it's not, it doesn't.
So where is it? TD physics?
So that, well, that's how you can email me to get it.
Okay. You actually need to put this on your YouTube channel.
There we go. Okay, so if we went to stairs. Sorry for my good friends up in Northwestern Ontario, we're just getting a couple things up here. So what we're doing right, there you are. So we're just reviewing where to get some of those videos of what we've done. And so the resources, secondary, grade 9 current electricity. Say we go step 1, simple electric circuits. So this is going to be a bit of a stretch to see what our bandwidth is like. So you're going to see Doug DeLamater and Dave Erb, and they're doing the same model. And so this was done with a video camera with someone floating, which was a bit easier than with a computer. And so you may be able to see with a little bit more clarity, if you've forgotten what has happened in the session, how this actually works. So for those up in Northwestern Ontario, the room has gotten pretty empty at this moment. And so we're going to work with some electricity models here at the tables in case you're unfamiliar with how we build. So we're going to set that up right now. Okay, so I don't know if you want to set that up with who is actually staying to build the circuits at this point. No, please go. If you need to go, you need to go. Where are you guys? You staying to play? Or?
Yeah, actually, no, yeah, I can.
Perfect.
Yeah, actually, no, I'm thinking of making. Where's the
The whole video's up on YouTube.
So,
Perfect.
At the back here, we've got our map.
Are you around?
No, at some point.
It'll take me a while to pick up. So Hamilton will be upstairs.
No, you have to walk down. Sorry. You're up here, so you walk around, down, up the stairs here, and then you would find your place over there.
Yeah, I want to get those. I want to get somebody who has a Flint. Are the Flint guys here still? I didn't see
I saw James earlier.
there.
Their booth is torn down, but you can still kind of make it friendly with people, so.
Yeah, okay. I didn't see them. I didn't see them. I want to get.
Is there a file?
That's this has been wonderful. I gotta figure out how to call this down a little bit.
Oh, you do have one.
Didn't have enough for everybody.
I gotta figure out how to bring it down a bit.
Yep.
For the grade 6s. I might not do the energy drop because that will be hard for them.
Sure.
But, there's some, I really appreciate you.
No worries.
What were you planning to do?
We're just going to build series circuits, parallel circuits, particularly working with multimeters and just going over common student mistakes, which I'll do for friends up north. Ed, want to stick around? We can do that.
Ah, mais merci.
Je peux essayer pour faire ça en français, mais c'est le probablement difficile.
You actually got all these things. You actually screwed into your blocks over there.
We assume, we try to make a model that was affordable for anybody, because assuming
you sell this.
I don't sell them myself.
No, that makes some sense. The model you have there is really good. I gotta figure out how to do this.
Yeah, so I mean, like, this is what I have in my lab. It took me a decade to get a class set. So it's wonderful. It has a short circuit light.
Okay.
Might as well include good people up north.
You can do the short circuit with this?
Yes, and when it does a short circuit, it makes a yellow dot. That makes it very unhappy.
But you're not breaking the machine? Or?
No,
okay.
It's designed for it.
Okay.
So this yellow dot is the reason I can teach project-based learning in a classroom, potentially without a TA, because this takes away half of the difficulties of building the circuits.
Okay.
Because short circuits are the most common reason things aren't working.
Yeah.
They're also an expensive thing eventually on your batteries.
Okay. And I have some, but they are older. Is this
Depends on the model.
New ones that have this feature?
There's old ones without. There's new ones without.
Can you do like for your battery example? Can you do it with this?
No, because the short circuit, you'll see the number drops down very quickly.
Okay. Well, thank you very much.
That fuse, the little fuse that you use.
Yep.
Was outside?
Less than one.
Less than one?
It guaranteed that it died.
Okay. I can actually stick around.
Oh, great. Okay, so let's see if we can get this angle. Here we go. Okay, so one of the adventures when you're working with these, is there any way that we can get this kind of further back and looking down? People don't have to admire my chin the entire time, but can, there we go. Perfect. Okay, so we go through a series of 3 models with our students, or 3 cycles with them. So a simple circuit with just 1 switch and 1 bulb, and they get an introduction to ammeters and voltmeters. For the equipment that I use, these are Mastercraft. So they come from Canadian Tire, which instead of it being a specialty electronics item, is available in most Canadian centers. If you are patient and wait a little while, you can see these go on for about $10. I'll show you real quickly that it comes with a kit, which is very nice and modular. And so you get a multimeter, you get some leads. The leads aren't great, but they work. Tell the kids to be gentle with them. I've replaced most of mine over the years. They come with wire strippers that aren't currently present and a pair of pliers. At TD Christian High, where I work, we do a lot of project-based learning, and having a whole bunch of tools at an affordable price is good. So the simplest system right here. One of your other adventures to be working with is the fact that you get wire spaghetti on a regular basis. And there's a lot of commercial solutions for that where you get clip circuits. The trick is that wires generally don't come in clip circuits in most of real life. So some solutions to this, sometimes I'll get hair elastics, and I'll get kids to bunch up most of the wire and put a hair elastic around it like this, so they have less spaghetti kicking around. The other possibility is to try to do, you can generally get a fair number of these for relatively cheap. I think next resource I have to explain to you, I got my catalogs quickly enough. Oh boy. Sorry, not sure what my source was on that. Shop around. These can be as cheap as 30 cents each or as much as $1.50 each. So what I do is I try to buy as many as I think I can afford, because the beauty of this is that if you have, say only red ones and white ones will be positive, and only green ones and black ones will be negative. It'll help organize the kids' thinking. So that's the easiest circuit we can make. I'd suggest when you make switches that you use the plain old $1 indestructible switches from Home Hardware. Some fun ones with this is that kids will love to attach it to the drywall flange right here, and they'll put that as part of the circuit. So I've put my 2 whites together, and black and green are going to be negative. And so they're going to be all excited. Sorry. There we go. And they'll say, hey, this isn't working. That's because they've attached it to the flange. So common student mistake number 1. So they have to get onto the pins right here. So that's solution number 1. Next adventure is that they have to add an additional bulb to this. Actually, we're going to back up one. They have to learn how to use a multimeter. And so I've got a simple circuit video, which includes ammeters and voltmeters. It's on my TD Physics channel. I assign my kids to go look at it before they do the lab. That means about half of them will actually do it.
Dave, can I ask a question?
Yeah.
It's Matt. I'm wondering, like, when you get them to watch those videos, do you do any of that before doing the circuit model, or do you usually start with the circuit model that you showed us earlier?
I start with the circuit model.
Okay.
Yep. So assuming that you have used these before, if you haven't, most multimeters will have a cord that goes into the center. It doesn't have to be black, but for convention's sake, we're going to do that. And then on the one side, one other lab thing, buy the cheapest batteries you possibly can to go into a multimeter, because kids will throw these back into the box. I give the kids a mark at 10 at the end for like just being neat, tidy, and safe. That includes washing their hands after working with electrical components, especially when we do project-based learning and they've taken apart unknown electronics. I just want to make sure that they're not ingesting stuff at lunch. Or during math class when they're licking their fingers. So we've got a voltmeter set over here. So when they put things away, they'll kill the batteries, and you're less cranky if you put a $1 store battery in there as opposed to like a $10 Energizer. So if it's going to be a voltmeter, I tell my kids to do the voltmeters last because you don't have to break a circuit to make a voltmeter work. So we'll get that operational, and let's see if we can get this set up so that you guys can see it. Yeah, I see the numbers there. So we test either side of it. Next adventure, so this one says negative, okay, I'm looking at it in reverse, but it'll be -5, I think it says. Negatives, that'll be the next big question from students. Mine says -5 volts. Well, here's the magic trick to that one. Switch to the other side if you've never done that one. It goes away. The analogy I tell my kids is, well, think of it as an energy difference, whether you're looking down Niagara Falls or up Niagara Falls, it's still so many meters high. And so it doesn't really matter. And the same thing is going to happen for our ammeter. So ammeter, I usually, one other thing is that there's settings for 20, 200, or 1,000. And so that just matters with how many decimals you get. And so depending on how much explanation of real life you want to do, and you just want to keep things simple, then your light bulb and your battery will read exactly the same thing. If you leave it at 20 and you do voltmeter testing, so I'm coming over here to the battery and touching there and reading about 5.1 or so, 5.1. If I come to here, almost 5. Well, what that means is that our wires actually do take a tiny bit of energy. They're not superconductors, they're just conductors. So if you're okay with explaining that, and I do like that one, so I let the kids set it on a more sensitive level. Usually it's nice to give them 1 decimal because they get really hung up on these centivolts, and that's not helpful in grade 9.
We were actually talking about how when you were showing the model, how you could compare the potential difference around the battery and around the light bulb, and it looks the same, like they're holding the blocks at the same level, but that if you were really to get into it using components, you'd probably see a tiny difference. So that's neat.
Absolutely. There would be a slope.
Yeah, cool.
Agreed. So ammeter settings, sorry, we're going to twist it around to the other side where it says 10A. It'll also say 10A on your multimeter right here. And so that's set up now as an ammeter. And with the kids, ammeters are so much more work because you have to break the circuit. And so for their first lab, they're going to have to break the circuit at green, they'll have to break it at black, they'll have to break it at white here. And I have found that if I use a few extra wires to kind of open up the circuit, and I try to put as many desks together as possible, hopefully you have unsloped ones in your lab, that allows you to have just a bigger surface to spread out your circuit, and the more spread out it can be, the easier it is to see what's going on. If you get really spaghetti syndrome going on, it's not great. So if we throw this in here, let's see if I can read backwards. Is that 0.23 or 0.53? I'm not good at backwards reading.
0.23.
0.23, beautiful. And so if our amperage is 0.23 there, what we learned in our model is that in theory, it should be the same everywhere. So if we come over here and test it at the switch, 0.23. A couple things that are fun to do while it's on. Flick the switch. Hey, no amperage. Put it back together. How about over here? right between the battery and the switch. And it should be 0.23 as well. And again, with rounding, it'll go to like 0.22 or 0.24, and the kids will freak out and say that's completely different. And you have to convince them that close enough is how physics works, at least in grade 9 electricity. So that's a simple circuit. Common mistakes that'll get made. Well, kids will take an ammeter and treat it like a voltmeter. And so this happens. Why are we not having bad things happen? That's weird. That should, oh, we're shorting out a switch. Never mind. If I do that, that just means that the switch won't work anymore. But if I do it here, there we go. Haven't had enough coffee yet today. This is causing a short circuit. You also see that the amperage goes quite a bit higher than it was before. Right, so instead of being a fraction of an amp, I think we're getting up to 2.5 amps or whatever. And the light bulb goes out. So when you're talking to your kids, if they're using any of the meters and the light bulb goes out while it should be hooked up, then they're making a short circuit, and that's bad. If you have a decade to ask nice questions of your department heads, this little piece of joy has saved me countless tears and frustration because it has a short circuit light right here. And so when my kids somehow make a short across these two terminals somewhere, usually in a parallel circuit, simple circuit and parallel circuit, not too bad. But once you get to parallel circuits, like it's just short circuit land everywhere. Because any mistakes in it usually result in a short. This bulb turning on tells the kids, stop, first of all, and try something different. And that's my requirement before I come and help them, is that they've done some troubleshooting. And that saves, plus short circuits aren't always real obvious. So that helps. Let's throw another light in. So again,
how much does this cost?
I don't remember, but in the kind of 200 to 300 range.
Each one.
Each one. So like I said, it took me about better part of a decade asking my department head, hopes and dreams. 1 year I got 2. It was amazing. Wow. They worked really hard to get it to where we needed to get, but it took time. Yeah, if you work at a school where you get a class set of those handed to you, Robinson at tdchristian.ca. Just kidding. I love my school. Don't fire me.
What's the damage on a low voltage power supply like that?
Oh, that's a 200 to 300, if I recall correctly. Okay. So this one's by Sigmatron. Someone who's less excited with a laptop there might look up sigmatron.probably.com, and they'll have a list of tech toys like that. So here we've got 2 of our bulbs that are hooked up in series. And so we're going to start playing with the same tools we did before. Brain like Swiss cheese. What was our amperage for just the single bulb? Like 0.2 something?
0.23.
Ooh, definitely Awaken Thunder Bay. Bonus points for you. Okay, so we got our 2 bulbs. They're lit up. They're going, and your feed is in the way. So I can now see it's 0.16. Good. So that's gone down from what it was before. Light bulbs are not ohmic resistors for those who really, really like physics. So they don't do the V equals IR relationship real tidily. It's kind of dependent on how hot they are. But the general trend that the kids need to see is that as resistance goes up, it's hard to go through 2 bulbs, harder to go through 2 bulbs. So therefore your amperage is going to drop as it goes through 2 bulbs. And they're going to do that a couple of times. So they're going to take the ammeter out, and they're going to break it somewhere else. We're not going to do that everywhere, but we'll do it a couple of different places. There we go. And so still, there we go, 0.17, which is the same thing as whatever it was before, plus or minus a centa-amp. The switch controls everything still. And we talked in our model, what happens if a light bulb gets unscrewed? They both go out. We did talk about what happens if a bulb is bypassed. So I'm set as an ammeter right now. So this is an example of kids making mistakes. So this is set up as an ammeter. They're testing it as if it was a voltmeter. And so this one goes out. The other one gets brighter. The other thing that we see is that our amperage is back to where it was, about 0.23. And we can do the same on the other. And if we do that at our battery, I'm only going to do this very, very briefly, but that's going to send both of my light bulbs out. And it's going to send my amperage spiking very quickly if I let it stay for any length of time. So that's series circuits. And it's not until you really get to parallel circuits where things get really interesting, because if you can get a senior physics student or two of them, I've currently got two grade 12 students who are on spare during my electricity class. And I basically said, you guys are about to go to university and could use some reference letters. I write really good reference letters. And for people who have helped me a bunch, you mess up on your time schedule and need one by this evening, I'm your man. Consider that when I make the offer of coming to help me for physics. They're both in there helping me for physics, which is great. So here's the trick with parallel circuits. And with with the resources that we give, it is nice in that it gives some of the more complicated versions of this. So your simplest parallel circuit, so I'm going to put greens on this side. And I said I was going to make things less complicated by trying to do color coordination. So we're going to throw some whites on the other side. And so there's your simplest circuit. And that works. So hopefully you can see that those are as bright as they were before. So that's the theory of how that works, equal voltage. And you're going to get some amperage splitting. And the amperage will actually be higher on the main branch here. But the problem with this setup with your kids is that where's the branch point? Now, in the resources that we give, we do teach the kids to learn that the branch points will result in lines of equal length, and that length on a schematic diagram means nothing in terms of reality. It just keeps things tidy. So what I ask the kids to do generally when they build their circuits, and this is why I try to give them as much wire as possible, is so we're going to separate out the branch point from the contact to the bulb. So we have our branch right here. And we'll grab another white wire over here, and we're going to stretch that out as well. It's just going to make it a lot easier for the kids to see where their ammeters are going to get stuck in to the circuit. And again, this will start to look increasingly spaghetti-ish as we go. Hence the wire colors hopefully helping. Let's bring battery into view. There we go. So the whites are going to be on the positive side, greens are on the negative side. So now it's going to be hopefully easier for the kids to see where to put different things. So either I try to get the kids to do all of one type of meter at once. Voltmeter, because the circuit doesn't have to get broken, is by far and away the quickest. Let's see. Yep, there we go. So that's just a matter of touching either side. And when I say voltmeter, I just did one of the very common mistakes that students make. You switch it on one side, but not at the base. And basically, if a guy who's been doing this for nearly 2 decades makes a mistake, kids will too. So the volts are about 4.4 right there. And in theory, they should be the same over here, but you'll find that, unfortunately, they tend to be, that was a little less. Wonderful. Okay, so our bulbs are not, at a buck a piece, these bulbs are certainly not going to be identical. These ones are close enough that you can't tell by brightness. But 4.3 here and 4.4 over here. And then back at the battery, it was more than that. And because my brain is a sieve after 3 days of presentations. Okay, so it's about 4.5, 4.6. So the wires have taken some. And one of the trends you will often see if your bulbs happen to be identical is that your far bulbs will get a little tiny bit less amperage. And that's because wires eventually add up to a bit more resistance. So the voltage is really easy when they stick, relatively easy. So when they go to ammeter land over here, that is a lot trickier because they have to break the circuit a bunch of times, and where they break it matters. So we test the one bulb and emphasize to the kids that when you are testing a component in a circuit, if it doesn't stop working while you're getting it set up, you didn't break the circuit and insert the ammeter in it. And so you may refer to your ammeter in class, say, you know, so-and-so was the ammeter, where was the ammeter in the circuit? Yeah, part of it. It was in series with it. And that language of series and parallel develops as you go along in the course. So 0.24 amps right there. We can break a couple places. We can break right at the light bulb. We can break at the branch over here. I'm I'm going to do it at the light bulb just because it's a little easier for me. Oh, sorry, I had this flop down. Okay, so we're finding that it's a slightly higher amperage right there, but we're in the 0.4, 0.5 range. And so if we take this and we go stick it here right at the battery, we should find that it has to supply both of those branches. Okay, so that was 0.4. Can't remember my other number, so I'm going to go back real quick. So that's 0.46. And so that should get split over here at some level. So 0.22, which means I should have 0.24 left over here in perfect amperage land. There we go. So these two amperages add up to what we have right here. So that's the basics of doing this. And now we can start adding things that kids frequently screw up and terrible questions that are hard to answer, unless you guys have any other questions with the regular mix-ups that students do. We have 2 people left here and some people left here. That's good. Haven't lost everyone. Move on to weird things kids do. We're good to move on to weird things kids do. I would take that as yes. It looks like you've got a mute on. Okay, I'm going to throw a couple more green and white wires into the mix. Okay, so here we go. Okay, so we are going to get our third bulb in parallel. It should also be equally bright. There we go. And we are in range. Excellent. So that's the extent to what the Parallel Circuit Lab and the STAO adventure will do. So common mistakes that kids will do is put branch points at the wrong spot. So here's a fairly common one that gets made. Let's see. So what I'm going to be doing is I'm taking the bulb off of a branch, a side branch, and I'm going to go stick it on a main branch. Okay, here we go. So this will frequently happen where you will get this. Okay, so this will require some convincing that there is any signs of life going on in this other bulb at all. Okay. We're doing a bulb switch. Ta-da. Thank you. Good idea. Okay. This leads us to the next adventure of things that screw up. Kids are really bad on wires. They go to clean up and they're like, and they will simply like T-Rex it style until everything crashes down around them. And so what ends up happening is that often you get wires that are hanging by a thread. So that's there's actually one really primitive way of testing this. If you short out a battery really quickly, that's not a STAO endorsed activity. But if your bulbs go out, that means that that wire is good. So my other question is whether or not this one was good. Okay, it shorted out things as well. So in theory, I'm doing a good job of screwing up like students do. Okay, it's on. This is going to require some convincing. Hopefully you can see that there's a glimmer in both of these. If you can't see that, you'll have to take my word for it. So there's a very, very dim glow in each one of these.
Yeah, we can see it.
Oh, good. And so what ends up happening here is that you've got this bulb on the main branch that's doing great. And you got 2 sad little bulbs over here. There's something called Kirchhoff's laws. Some of you probably have advanced degrees in physics and have done this until you're blue in the face with epic problem solving. Others are like, who? they get into some really beautiful things that some kids in grade 9 can do. They have to be comfortable with math and good with logic. So you need a way that, like, an applied kid asks you, why on earth is this happening? So without getting into Kirchhoff's laws, what you can say is, well, every single Coulomb comes through from the battery and has to go through this bulb. And then it splits off here and goes to 2 different bulbs. Technically splits it there. So that means that this has more amperage than those branches right there. So every Coulomb has to come through this one, but not every Coulomb goes through these. And the other piece is that this one's going to get a share of the voltage of every single one of these. And now they don't need to know why it is, but if they set this up as a voltmeter, what they need to know is that power is equal to amperage times voltage, or just brightness is equal to amperage times voltage. In terms of kids understanding grade 9, how much food you get per day depends on how many meals per day and how big are the meals. And so if you snack all day long, that's like having low voltage but high amperage. Maybe you just have like one mother of all meals. That'd be high voltage, low amperage. If you have high both, then that's lots of food. If you have low both, that's not very much. So here, our voltage is about 4. Remember that was only about a 5 and a smidge battery. So if this has 4 and that has about 1.5, that means that it's getting more food per plate. And every single plate comes here, amperage, but only half the plates go each way here. So you have high voltage, high amperage, high brightness. So those are ways of explaining somewhat complicated physics in simple ways that grade 9s can understand. So those are common mistakes that grade 9s make, some fun twists they throw at you, hopefully some ways of explaining those and fixing them. I'd love to hear any other questions that are coming from the Northwest. Howdy.
Our mic on. Can you repeat? Sorry,
Sure.
we're just turning our mic on. Can you repeat?
Sure. So that's a whole bunch of mistakes that students commonly make, some ways of fixing them or explaining what they've done, the physics behind why they work. And so are there any other questions from you guys up north?
Just one thing, Dave. We were just talking about just now the language in terms of voltage.
Yes.
How voltage drop, voltage difference, potential difference, all those different terms can kind of get thrown into the mix and can be kind of confusing.
Yep.
Any advice on how to talk about voltage or what kind of terms to use in order to make that clearer for kids?
I generally avoid the term potential. In grade 11 physics, that's absolutely essential language. It's either potential or it's essentially kinetic in some form. Mm-hmm. So it's either nuclear potential, chemical potential, gravitational potential, elastic potential, or it's moving or hot, which is just a small version of fast. But in grade 9, the issue is that even once kids take grade 11 physics, very few of them are, as a percentage, are going to go on and that'll be an essential part of their lives. Your percentage in grade 9 is really small. And so if they understand the idea that that voltage is simply energy that is coming from the battery that's given to the coulombs and is then, the one piece I do try to avoid is talking about energy being lost, or especially not destroyed. Like it's just changed into another form. So that's language that I want my kids to at least be capable of for me when I see them in grade 11 physics.
Right.
Cool.
So
I talk about voltage as an idea and then reiterate that voltage, what voltage is energy given per coulomb.
Okay. Thank you so much for the session and for taking the extra time to work with us. That was awesome. I got to do this one years ago with Dave Erb when he came to Thunder Bay. But my student here, Hope, who's behind me, is about to start doing this in her placement next week. So I talked about this, but this was tremendously helpful to let her actually see the stuff in action.
Yeah, you got a friend in the shop that can make a whole bunch of little blocks like this?
I don't think so.
We'll see what kind of gear the school has. Hopefully it's a good setup. Anyway, thank you so much, Dave.
Yeah, thank you.
Really appreciate it, and thanks for taking your weekend out to teach us some stuff.
Thank you for coming on your weekend to come learn. Let's work together.
Awesome. Is Brennan around so we can say goodbye, or is he?
He's smiling, and here comes his beautiful visage.
All right. Bye.
That was awesome. Thanks for coming.
Thank you so much. This was great. Oh, I mean, obviously we'll talk later, but the tech worked way better than I could have hoped. You know, the audio was good, picture was clear. Even when we were looking at slides and hearing the presenter at the same time, that worked super well. So it's so much potential here for reaching the North, reaching broader audiences. So thanks for all your efforts on your end to get this up and running and make it happen.
No problem. Thanks for your enthusiasm. Raquel just kept on saying there's this really keen teacher in the North, Matt, and he really wants this live stream to work. So we've got to make it happen. So
this is all good things come from Northern Ontario.
having the audience like wanting to try to tune in this way just made us work that much harder to get it done. So hopefully we can tune in to some more audiences. I mean, the YouTube live stream can handle 1,000 schools, 10,000 schools. So, but for participation, Google Hangouts works really well. So looking forward to building this with you.
Yeah, cool. Okay, we'll talk again soon.
Awesome. Have a good weekend.
Thanks, Dave. Thanks, Brennan. Bye.
Thank you.